Temperature and molecular velocities. According to the kinetic molecular theory, particles of different masses have the same average kinetic energy at a given temperature. So as long as you maintain the same temperature, even if particles have different masses, they weigh differently, they should have the same average kinetic energy, because this kinetic energy equation summarizes this relationship. Kinetic energy equals 1/2 mv squared, mass times the velocity squared. So here's a nice graph to show you that the heavier the molecule, right, tends to move slower than lighter molecules. So basically, if you have a massive molecule, its velocity will more likely to be lower. If you have a lighter molecule, the velocity will be higher, but its mass is lower, obviously. I like to give you an analogy, and then I'm going to show you the simulation here. It's kind of like thinking if you have a semi-truck or school bus, whatever it is, and you have a, just a regular vehicle, a sedan. They both have different masses. You both agree they have different weights, different masses. But in order for let's say the car to have the same amount of energy as the school bus or the semi-truck, if it can't make it up with mass, what should it make it up with? It should make it up with the speed. So they have different speeds or velocities. So while this may weigh, something like 5 tons, this one might be 2 tons. This one can be flying at, let's say, 150 miles per hour. This one can be at, let's say, proportional. Let's say it's about 70 or 60 something, 60 miles per hour, to give you kind of an idea. So that's what, make sure you understand the relationship here, is that heavier molecules tend to have a lower velocity, they move slower than lighter molecules. So let's give you an example here. So I have 2 types of particles. I can add them to this chamber right here, this vessel. It's going to tell me the pressure, the temperature, etc., and of course the average speed. So if you look here, I'm going to add, let's say, 10 particles of this heavy molecule right here. So as you can see, if I leave it at just close to room temperature, I see the kinetic energy here. Now, I can now add also 10 particles of this. You can see that the kinetic energy kind of doubled again, because you have double the number of particles, but it did not change like in terms of being different. So maybe it's better if we isolate this. So let's actually just start over here. Here we go. So here's 10 particles. Temperature 300, pressure is right there. Now, if we just erase this and now do of the lighter particles 10, notice that the kinetic energy is the same right here, down here, but they are moving faster. So their speed is higher. Look at this, 1,368. Okay, it says basically molecules per second. And if you look at the other one, go back to the other one, and if you look at the speed, it would be 517. It would be at 517. Okay, meters per second, I'm sorry here. So that's the idea, okay, is that they do not change this way. Now, since we're here, we're also going to talk about the next and final topic, which is real gases. Real gases, they deviate from ideal gases. So ideal gases assume that if we go back right here, they assume that volumes of all molecules of gas is negligible. We're going to challenge that, and there are no attractive or repulsive forces. We're also going to we will also challenge these two. So 2 and 3 is that the volume of all molecules is negligible, but and there are no attractive repulsive forces. They don't attract or repel each other. We will find out that those are actually not true when we change some conditions. So let's show you. So you need to keep in mind that the assumptions break down at higher pressures or lower temperatures. So we say real gases have finite volumes and they do attract one another, meaning that the molecules can attract one another. So let's look at this example. It says the volume at low pressure, the volume of a gas molecule is negligible compared to the volume of container. But when the pressure increases, the free space at which the molecules can move becomes smaller fraction. So let's look at this. Here's a beautiful example. This is a cylinder and a piston. Piston is what goes up and down, this part right here. So if you have a large volume, this is a large volume, which means you have a low pressure. Remember the Boyle's law equation. That means that, yeah, it doesn't matter how much volume they occupy, these molecules. But the moment we actually decrease the volume by increasing the pressure. So you notice here, you agree with me that if you push down on this, the pressure is going to increase. That there's less space here, less space. So therefore, now these molecules, if you look at them, they actually occupy a bigger volume and the volume is no longer negligible, okay? So we say volume of molecules cannot be ignored at high pressure. And we see here that at low pressure, it's closer and closer to the ideal gas, but at high pressure, look how it moves farther away for each gas, moves away from the ideal gas. The other one is attractive and repulsive forces. Attractive forces are positive to a negative. And of course, repulsive forces are negative to a negative or positive to a positive. We say that those actually do play a role. But when? When? they play a role at low temperatures. Think about it. When things are moving very fast, I'm going to show you back here. When things are moving very fast, let's increase the temperature. So we're going to increase the temperature, and you're going to see how when things are moving very fast, they don't have enough frequency for them to actually attract each other. They're moving very, very fast. They zip by, they can barely feel each other. So that's why we say at high temperature, it doesn't apply. It more behaves like the ideal gas law. But the moment you cool this, the moment you cool it, so look at it. Oh, pressure is too high. The moment you cool this, and let's actually, look how they move now they start moving very, very, very slowly. So when they zip by each other, they can attract each other more effectively or repel each other more. Versus when they were moving fast, they didn't have a chance to attract or repel each other, but now they can, although it's not shown here. So that's what we mean by low temperature, and then they can actually interact with each other. Like right here. When it's low temperature, the red can be attracted to the blue, and they can barely strike the wall of the container. So it's going to have, again, an impact on the pressure. So less forcefully, this is the wall of the container. And again, you see it here. It says attractive forces lessen the impact of a given molecule with the wall of the container. And once again, the lower the temperature, the higher the this is the pressure right here. Talked about that. The higher the temperature, the more, so look at the temperature, the higher it is, the closer it is to behaving like the ideal gas. But the lower the temperature, the farther it is away from behaving like an ideal gas. So that's the idea that we are trying to portray here. So this is high temperature. This is low temperature.